Physics and Astronomy and the Minnesota Institute for Astrophysics welcome you to a summer of Astounding Astrophysics. Normally I introduce the speaker, but Emma DeBruin, who is a graduate here and is now working for Michael, and consequently she said she has nothing but good things to say about him. And she will introduce him, and then we'll have a talk on catching some gravitational waves, in honor of which I wore my Silver Surfer tie, so we do a little surfing later on. All right, there you go.
Hi everyone. So this is Professor Michael Coughlin. He joined the University of Minnesota in January of 2020, kind of perfect timing for that, and recently became an associate professor in May. He's an active participant of the Laser Interferometer Gravitational Wave Observatory, or LIGO, collaboration, the Zwicky Transient Facility, the Palomar Observatory, Ferris C. Rubin Observatory, Legacy Survey of Space and Time, and Kitt Peak Observatory Spectral Energy Machine. So quite a bit going on, and he plays a significant role in one collaboration. Like, not only does he play a significant role in one collaboration, but he does so in many very smoothly.
Thank you. Can folks hear me? Okay, sounds like it. Huge shout out to Emma. She learned like 2 minutes before we were going to start that she was on the hook for introducing me, so big shout out to her.
You can take the tape off that chair.
Yeah, I'll just go back to the Rubin slide for a second. There's a few folks in this room, some sitting here, Emma, Christina, Tyler's in the back. Many of my graduate students, undergrads, working now on Rubin, which literally just last week has started to release data. And so thank you to my people who are here taking their time away, as I also put pressure on them to analyze the data as it comes out in real time. Okay, but we're mostly going to be talking about gravitational waves today. So as Emma mentioned, I'm a member of the LIGO scientific collaboration, and so we're going to be talking a lot about how we detect gravitational waves and the kind of science that we do. And of course, I want to first thank the funding bodies that make what we do possible, the National Science Foundation, which funds LIGO, as well as many of the ground-based observational facilities we'll be talking about, and NASA, which funds all of the space-based facilities. And so, for those of you who haven't heard about gravitational waves, it's actually a relatively new field. So I started as an undergrad back in 2009, studying gravitational waves, and back then they were only theorized and hadn't actually been discovered. And it wasn't until 2015 actually that we detected gravitational waves for the first time. And so this field is actually less than a decade old, relative to astronomy, which has been going on for eons, of course. And to give folks a little context, what are gravitational waves? So, just for intuition, there are waves all around us, right? So, for example, waves in the water, waves in the ocean. It turns out that ocean waves are actually the loudest source of seismic waves anywhere on Earth. You can detect ocean waves from even here, flat Minnesota, where you put a seismometer down and you can detect them. And so, and of course, there are all sorts of beautiful images, up in clouds in the atmosphere. And so the way I typically go about describing how gravitational waves work is first building that intuition of, you're sitting by a lake and you toss a little rock into the lake and you get those ripples. And so these gravitational waves are going to turn out to be these ripples in space-time. And so as I mentioned, this is a relatively new field, but folks have been thinking about how gravitational effects work for the last, since the 1600s or so. And this brings us to Newton. And so many folks have probably heard the apocryphal story where Newton sitting under a tree, apple falls from a tree, and he thinks about, why does gravity work the way it does? And it turns out, just from this thought experiment, he was able to understand a lot about, for example, how the solar system works. Just using basic Newtonian mechanics, you can understand how planets interact, how orbits work. And it actually worked, this theory worked very, very well until the early 1900s. And so it wasn't until a different thought experiment, this time by Albert Einstein, and let's say one of the problems that you have with Newtonian gravity, how does action at a distance work, right? So if for example, I was to sort of snatch away the sun, according to Newton, immediately, the Earth would kind of fling out of orbit. But Einstein was thinking, what would it look like if I was to actually sort of ride on the back of light? And so he realized that there's some kind of cosmic speed limit that turns out to travel at the speed of light. And it turns out when you work this through, gravity doesn't just happen instantaneously. Gravity happens in this, what we call space-time. And so you can think of space-time. So if some of my students were hosting something like 25 eighth graders last week here, just in the lab, and as part of this Eureka program, and to try to explain to these eighth graders how gravitational waves work, what we do is we have this spandex sheet, and we put this big marble ball in the center of the spandex, and we have them throw marbles, and you can kind of see how these marbles are orbiting, and then they make these little ripples in the spandex. And this is really how you can think about how space-time works. So here I have, my space-time sheet. It's like this, ruled paper, just like you would have in some kind of geometry class. And here I have the sun, or a black hole, or anything else that's large, and it's warping space-time. And so kind of the classic quote that we use is, matter tells space-time how to curve, and space-time tells matter how to move. And so what's happening here is that as large objects, they sit in space-time, they're curving space-time, and objects are literally falling through space-time just based on the curvature of space. And so of course this idea might sound crazy, right? So Einstein's sitting around kind of early 1900s thinking about this, but as one of my old professors likes to say, if a theory can't be tested, it's not science. And so it turns out that this theory could be tested, and one of the ramifications of Einstein's theory of general relativity is that even an object as large as the sun should deflect light. Like literally the light, which otherwise should be traveling in straight lines through space, it's going to be deflected off of its path just a little bit. And so you can actually see stars that appear to be in the wrong place just because light is bending around our sun. And so it turned out that Eddington, back in 1919, of course he had to do this during a total solar eclipse, but he went on an observation run where he went and identified the displacement of a star, the apparent displacement of a star by the sun, and so this was a big deal because it was confirmation of general relativity. Now, this was a big deal, right? So Einstein, sort of sitting there doing this thought experiment and sort of writing down the equations for general relativity, had predicted, sort of how gravity should work. But we haven't really gotten to what I'll call astronomy yet, right? So, we're really interested as astronomers, like what can I try to understand about the universe beyond the physics of how gravity works? And so one of the first effects that we astronomers were able to use to try to understand that general relativity is useful as an astronomy experiment was this Hulse-Taylor binary pulsar. And so What a pulsar is, if I take a really, really compact star and it's spinning, these stars are something like 1.5 times the size of our sun, but they're only about 10 kilometers in size, right? So if you were to take something like a teaspoon of material of one of these things, it's like 1,000,000 tons, something like this, all crammed into that one teaspoon. And so these are really, really incredibly compact objects. And so they're also really good timing instruments, because it turns out that they're emitting X-rays as they spin around, and so they're highly magnetic and they spin X-rays, and so you can actually watch the period of these two neutron stars over many, many years, over many decades. You can actually watch them lose energy due to gravitational waves. And so it's as if the orbit of the Earth and the Sun, you were just sort of watching the period change over time. And what's really amazing is that, so this is a plot of the change in phase on the y-axis and then time on the x-axis, and so you see there's something like 40 years. In red here, it's the measurements from this binary pulsar system, and this is not a fit, right? These are measurements, and this is the prediction from general relativity. General relativity, it turns out to be one of these great, true great predictors of how the universe works. And so this was particularly exciting because, back in 1919, Eddington, with his understanding of the eclipse, was able to understand that general relativity was correct. But this was the first confirmation that there were actually observable features in space-time that we could use to understand astrophysics. And so this was a really big deal and led to a Nobel Prize back in the early 90s. And so just to give you a sense of what's actually happening, so I have this pulsar system, it's losing energy due to gravitational waves, but what does that actually mean? So as these two neutron stars are orbiting one another and spinning, what's actually happening is that space-time is expanding and contracting as the gravitational waves move through it. And so if I was to take my spandex sheet sort of example, one direction would be stretching and one direction would be shrinking as the gravitational waves move through space. And so this is a nice little schematic that you can see. So in this case, the direction of motion would be this way, and so slowly but surely the undulation of these waves. This is literally space-time expanding and contracting as these things move. And so you might be thinking to yourself, what am I possibly going to do with this, right? Okay, so I have this space-time thing. It's indeed, I have these motions in one direction and contractions in another direction. Okay, what's really, what am I really going to do here? How am I actually going to turn this into an experiment, right? Okay, so some of you might have heard of the concept of interferometers, and so we'll play the movie in a second, but just to show what's happening beforehand. So the way an interferometer works is I take a laser. In the case of the lasers we're going to be talking about, we're talking about kilowatt kind of level lasers, and we're going to have a laser that goes out into a beam splitter, and what happens with a beam splitter is it splits half of the light one direction and half of the light in the other direction. At the end of these interferometers, I'm going to have two mirrors that are held to be, or are at about the same distance. And what happens is, as the light travels out to this mirror and bounces back to the beam splitter, and similarly bounces out to this mirror and back to this beam splitter, in cases where these two distances are the same, there's no light that comes out here. There's just deconstructive interference, and so I'll get no light out at the end. But in case where I have a difference in distance, I'll get constructive interference and I'll get light out at the end. And so let me play this little movie here. So you see the light going out and bouncing back. As these distances change, I will get output here, and I can measure this on, for example, a photodiode, and so I can track differences in distances as the light, as the distances between these two mirrors change. For example, if gravitational waves pass, right? And so I was just telling you that gravitational waves expand space in one direction, contract space in another direction. Interferometers are perfect measurement tools for studying spacetime, it turns out, or the gravitational wave effects on spacetime. So what interferometers are going to be doing for us is we're going to be measuring the difference in distances between these two mirrors, watching the distances change due to the gravitational waves, measuring the output on, in this case, a photodiode to measure their amplitudes. And so this is, so the concept of interferometers, though they're very old, they've been used to measure distances for a long time. The only real innovation here is we made them very, very large. How large? These are 4-kilometer scale arms, right? And so there are a handful of gravitational wave detectors in the world. One is in Hanford, Washington, out near a nuclear site. The other is in Livingston, Louisiana. And so, of course, these aren't exactly simple interferometers. They're, of course, held under vacuum. And so, as folks may intuit, building a 4-kilometer scale interferometer held under vacuum is an incredibly challenging technological task. And so the control systems that are used to sort of maintain the stability of the cavities that contain these lasers is quite incredible. And so what you're basically seeing here is every single one of the kind of key components. So for example, the beam splitter here, the mirrors at the very ends of these interferometer, they're held under these multi-stage suspensions to try to isolate the system seismically from the Earth. Right? So the big challenge of doing gravitational wave astronomy with interferometers is actually things like humans, right? Humans make noise. And so at Livingston, Louisiana, it's not even apocryphal. On Sunday mornings, you can actually watch folks drive to church, just sort of, in your gravitational wave detector. Because humans are the loudest source of seismic noise, right above 10 hertz or so. And so we within the US have built 2 of these systems. There's another one in Italy, another one in Japan, one in Germany. So there's actually a worldwide network of these things now. And so just to give you a bit further sense of scale, so this is, so of course, due to the sort of the sensitivity of the instrument, of course, all of this is done in clean room environments. And you can just sort of see the size of these seismic isolation chambers right there. It's taller than the people are. I also have a little video. The mirrors themselves, they're about a foot in diameter. So like it's for someone who did junior lab or MXP, as you call it here. The little tabletop interferometers that you build, this is not that, right? You've really blown it up. And so as I mentioned, we have this worldwide network, one in Hanford, one in Livingston, one in Virgo. We're building one in India. And we'll talk about in a little bit why we need so many of these to do the kind of science we care about. But before we get there, I just want to so this little movie, so this is an example of if I have 2 black holes that are merging. It's the gravitational waves that are coming away from these 2 black holes that merge. These gravitational waves are passing through the universe. Gravitational waves interact weakly with matter, and so it doesn't matter if there's material between us and these black holes. Of course, this is a giant dramatization of the effect that these gravitational waves are happening here on Earth, but hopefully you get the idea. And then, of course, then they pass through our interferometer. And so this is the concept for our experiment. And so, as I mentioned, it was back in 2015 that we discovered the first binary black hole system. And so the way that you can read this plot, so on the y-axis is frequency and on the x-axis is time. And so a few things to note. In frequency, it's these, in this case, these black holes, they merge at around 100 hertz. So in the audio band, you can literally, in some sense, hear the gravitational waves as they merge. And the time scales here are less than a second, kind of orders, 100 milliseconds for these two binary black holes to merge. And so you get this very characteristic whoop, this chirp that you get as these two black holes, they get closer and closer together until they finally merge here. So this is physically what's going on. And so in terms of the kind of science we can do, right? So it's cool, right? Two black holes far out in the universe, emitting gravitational waves, oscillating space-time, measuring them with kilometer scale interferometers. It's a cool experiment to be a part of. Big thank you to my graduate students for helping make all this work. So this is an example where so in blue is the data here, and then we have the prediction from Einstein here in orange. And by changing for example, the distance to the black holes and how large the black holes are, run a little movie here. So you can see here we're changing the mass of the black holes as well as changing the distance that are to them, and in that way we can match the data, right? And so this is the kind of astrophysics that we can do with these gravitational detectors. We can measure how far away they are. We can measure the mass of the black holes. There are other parameters as well. And so all of this led to a Nobel Prize. So Ray Weiss at MIT is kind of my academic grandfather. He was my advisor was his advisor, and so this is as close I'll get to a Nobel Prize ever, and then Kip Thorne was at Caltech, and Barry Barish was also at Caltech. Unfortunately, Ron Drever, who was one of the main instrumentalists on the project, passed just not long before the Nobel Prizes were given. So being around for the first detection, I would say it's been quite the same, party every time since then. Nowadays, we find a binary black hole about once a week, and so it is, almost commonplace for, being part of this was, going to my graduate students like, oh no, another alert on my phone, whatever. Life's changed a lot since then. And so you can see how we've really kind of changed what we know about black hole astrophysics back in, before 2015. So in black here are all the black holes that we think we know about electromagnetically. As you can imagine, even that's a hard experiment, trying to infer things like how large black holes are from like their companion, maybe if there's a star that's orbiting them. We've by more than order of magnitude increased the number of known black holes, and the measurements on them are much more precise than anything that's been done before. And we really have found an entire zoo of different pairs of all sorts of different masses and mass ratios, and it's pretty exciting. And so this is just another way to represent the data, but the distances here that we're talking about, gigaparsecs, sort of millions of parsecs away from us, and we see them. So here we are in, sort of summer of 2015, and it's, as I mentioned, it's a really, really regular occurrence. And so, black holes are interesting. As an astronomer, it's an exciting thing, but I prefer objects that I can go point a telescope at, and so we also detect, so I mentioned sort of at the beginning of the talk, these neutron stars, these compact stars that that binary pulsar that won that Nobel Prize. And so it's back in 2017 that we detected our first pair of binary neutron stars. What got us excited about this, so you'll notice that the y-axis looks pretty similar. You have this chirp-like track. It's pretty faint. But on the x-axis, the time is much longer. This is 30 seconds advanced, something like this. And the thing to know, or the way to interpret this, is that as the time gets longer, the mass goes smaller, right? And so we knew immediately after detecting these that this was not just another binary black hole system, but instead a binary neutron star system. And so as an astronomer, I want to be able to go try to point telescopes and go try to study these neutron stars that had merged. And so unfortunately, with just the gravitational detectors, they're a bit like radio antennae, and so they don't tell you exactly where to look. They give you kind of bananas on the sky, and so we use galaxy catalogs. And so in here there were, within this particular localization, we had something like 50 different galaxies to troll through, but astronomers took images of all of these galaxies and turned out to identify the right one. And so this was a big deal for us. And so what makes these fundamentally different is, unlike black holes, which are completely compact, there's no tidal disruption, there's nothing actually to see electromagnetically, neutron stars produce a lot of photons, both high energy photons in the form of gamma rays, all the way to optical photons that we can see with telescopes that we could even like up on the roof, right? And so, as I mentioned, after trolling through many different galaxies, we identified the correct galaxy. There was a team led out of Santa Cruz that did this, and saw this exceptional object. And so, let's see if I can play the movie. So here we are. So on the y-axis we have brightness, and the x-axis we have wavelength. And so this object we identified started really bright, hot, and blue, and slowly, over the course of about a week, faded, and features in the near infrared started to develop. And so this was unlike just about anything that astronomers had really seen before. We hadn't caught something like this in real time. And what makes this really exciting, the identification of these neutron star mergers, there's all sorts of cool science that you can do. So I'll just name a couple of them. So, for example, we don't understand well how matter behaves in really dense environments. Here on Earth, you can get to nuclear saturation densities of about 1 or 2, something like this, when you're at these ion beam facilities where they slam particles together. Getting to densities at like the core of neutron stars would just be impossible here on Earth, and so you can study really how matter works inside of these neutron stars using gravitational waves. Another kind of measurement you can do, so that's nuclear physics. You can also do cosmology, and so there's this crisis in cosmology right now where astronomers for a while have been trying to understand how fast the universe is expanding, right? So we know our universe is expanding, but how fast tells us something about sort of fundamental physics of how the universe works. And of course, since it's an interesting problem, a lot of different experiments have been tried, and there are kind of two main ones. One uses the cosmic microwave background, the temperature fluctuations across the universe, and so measurements from satellites like Planck and others, they get one answer. And folks who use these supernovae, these type 1a supernovae that happen in white dwarfs, they get another answer. And so astronomers have been racking their brains for more than a decade now trying to understand the difference between these. Is there fundamental physics here? Is there issues with calibration? Do we just not understand our supernovae particularly well? What's pretty cool is that Einstein's relativity gives us yet another way to measure the expansion rate of the universe, and we've done this measurement with this particular neutron star pair we found, and after detecting 10-ish more, something like this, we should be able to sort of break the tie between these. If you're not really a cosmologist, maybe you're interested in more fundamental astrophysics of how heavy elements form, things like gold. It turns out that merging neutron stars are the cause for the vast majority of the periodic table, the actinides, lantanides, and so on. And so the reason gold, platinum, and such exist. And so, studying neutron star binaries is how we understand how heavy elements form. And so all of this is, great, right? We can do all of this cool astrophysics, but, I've sort of mentioned, one object we found. Why haven't we found a lot more? Well, it turns out that measurement's really hard. And so on the y-axis here, I have these terrible, terrible astronomer units. I'm really, really sorry. I apologize to all of my, undergrads when they take my astro class. On the y-axis here, I have what's known as magnitudes, and it's a logarithmic scale because we see logarithmically. So it's a historical scale where more negative numbers are brighter. And so it's just, very annoying. And so on these black curves, I have a bunch of pretty common types of supernovae, so different types of stellar explosions and stellar deaths. And you'll notice that they get very bright relatively quickly, and they stay bright for months on end, right? So this plot cuts off at 30 days, and you can see supernovae. Rubin's going to see something like 10 million supernovae over its lifetime, and we'll see them for many, many months, right? So if you're interested in supernovae, Rubin's your experiment. But these neutron star mergers that we care about don't look like that. So in this red curve here, you'll notice it's much dimmer than these supernovae, and it fades much more quickly. You only get a day or two to try to identify these things, and so it's a very challenging experiment. But of course, there's literally billions of observations by telescopes out there. These neutron star mergers, they span all across wavelengths, and so there's a lot of telescopes out there. It's actually really a challenging data science problem. And so my group works on what's known as the Zwicky Transient Facility, and so it's on Palomar Mountain, which is not far from LA. Actually, kind of right in the middle of LA and San Diego, so I spent, 3-ish years of my life in Pasadena. Not a good place to build a telescope, but it is, it's far enough out of town where, it works pretty good. And just for scale here, so this is one of the largest, filter arms ever built, and so let's see if we can get it to play here. Maybe because of the way I constructed this slide. Oh yeah, I was just calling. Sorry, it's worth looking. So what's going to happen here is you have a filter arm. The way that we do astrophysics is unlike in your phone where you have basically a single chip has a red, green, and blue channel, we take individual colors at a time. And so we have to put filters in front of our beams, and so what you see here is the filters being changed in and out. And so this is an array of 16 different CCDs. So you have one CCD in your phone. You can see here 16 different very large formats of CCDs. So this is round numbers, 100 megapixel camera. And so we take observations with CTF. And just for scale, we have something like a terabyte of data per night. It's 6 petabytes over the past 6 years. We have over 1 billion sources. One of my graduate students, his whole thing is using machine learning to try to classify the 1 billion sources that we have in CTF. It's just a monumental task. And the other thing that makes this hard, while we're interested in these neutron star mergers, there's all sorts of other things that are happening in the night sky. So this is a little video where we show all of the mostly supernovae, these stellar explosions, that we have identified with CTF over the last handful of years. And so what you see here, so it doesn't cover quite the whole sky. CTF, it's in Palomar, it's outside of Los Angeles. We can't see through the Earth, so we can't see to the south. So this is basically the southern hemisphere here. And then the galactic plane, the plane of your galaxy, it's very hard for us to look through the galactic plane. There's all sorts of dust that Brendan would make it very hard to identify supernovae. So we don't really identify things either in the south or in the plane, but you can see, and actually this video stops in 2024, just last year we crossed that 10,000 spectroscopically classified supernovae mark. And so what happens is this is really a needle in the haystack problem. We're looking for these rare, faint, fast neutron star mergers amidst all of this, right? And so it's an incredible challenge to identify these. And so the one thing that we've done to solve this is we've built robotic spectrographs on telescopes. And so I have, we've built one of these things and put it on a telescope on Palomar. And just the last few years, so I'm PI for an experiment called the SED machine at Kitt Peak. And so it's a 2-meter class telescope at Kitt Peak, where we've put an upgraded version of these, and folks in my group work on this. And so one thing I just want to highlight here, since a lot of people are kind of thinking about, how does data science, AI, ML, how is it affecting astronomy? Back when I was a postdoc, I spent a lot of time staying up all night looking at data, right? That was my whole life for 3 years. And so you're up there, either you're at the telescope, or if you're lucky, maybe you're in your living room and you're logging into the telescope from afar, but you're still doing so many things manually. It was all very slow. As I said, I spent years of my life doing this. Over even just the last few years, things have really changed now, where we go from taking data with a telescope like CTF. We have machine learning-based filtering software, that same kind of thing I would do. I would look at the data during the night. Instead, I now have an AI agent that does this for me. I would identify the kind of objects I want to get spectra of, and then I would go and report to the community the identification of these spectra. We have mostly ended this process for those poor graduate students and postdocs who stay up all night. These days, we have more than 100 fully automated, fully robotic, no humans in the loop identification of, in this case, supernovae. We're really moving away from sort of this classic astronomer mode to folks really using data science to enable discovery. And this is essential with I mentioned CTF's at the kind of terabyte per night level. Rubin, which we showed that slide from in the very beginning, is more than 2 orders of magnitude larger in terms of data scale than CTF itself. And so, we actually need AI to allow us to make discoveries like this. And this is only going to get worse. As I mentioned, Rubin's at 10 petabytes per year. There are, radio surveys, SKA, for example, it's a petabyte per day, 300 petabytes per year. These are, the data scales are incredible. So what's happening now? We're just finishing, we're just in October, we will finish this current gravitational-wave observing run. Then the plan will be to turn our interferometer off and upgrade it over the next couple of years. And just looking a little further, look further ahead. So just like in electromagnetic astronomy, there's different wavelengths. There's different wavelengths of gravitational wave astronomy. We've been talking about astronomy in the audio band, but you can go to lower frequencies as well. And so I'm just going to highlight one experiment that we're hoping will eventually fly. And so this is known as the laser interferometer space antenna. You can kind of think of it as LIGO in space, one of these interferometers in space. But the difference is that while we have 4 kilometer scale detectors here on Earth, you'll have 100 million kilometer scale arms right out in space. And so you can you can measure kind of millihertz-ish gravitational waves, allowing you to do gravitational waves from intermediate mass black hole binaries, much larger black hole binaries, for example. Yeah, so I have a few more simulations here, but we're at 7:45, so I think we'll look to close up here in the next minute. I just want to kind of make the point, we are just at the beginning of gravitational-wave astrophysics. Even during the time that I was a graduate student, we've gone from not having any gravitational waves to having hundreds of identified gravitational waves, and those numbers are only growing every single day. We have, one way, so I know Lucy talked extensively about Zooniverse last week. My brother actually was one of the developers of GraviSpy, which is the gravitational wave Zooniverse project, and so if you're really interested in helping us identify gravitational waves, please check out GraviSpy on Zooniverse. It's a great project. We also, and if you have any questions, Christina, who's here in the audience, helps run Kilonova Catcher, and this is a project where we work with citizen scientists or amateur astronomers to be able to help us look for gravitational waves and their counterparts, in addition to all sorts of other cool astrophysical transients. Christina, raise your hand. Yay, that's Christina. And so this is, for those, let's say, astronomer enthusiasts in the crowd, this is a really cool opportunity. Otherwise, I just want to say thanks again to NSF and NASA for paying my people to, make this cool science happen. And otherwise, thank you to all of you for attending. Okay. And I'm happy to take a few questions, if you have any.
Yeah, I'll take that microphone and pick it up.
And please make Jim run up and down. This will make me happy.
There we go.
So, there is a theoretical concept known as white holes, essentially an area in space where nothing can enter. So my question is, what exactly would happen if you were to essentially push a white hole into a black hole?
It's a gray area.
I could never follow on that.